Look at this layout. Two separate horizontal roads, line L and line M. Watch as a high-speed track, line T, cuts diagonally across both. In math, a line that slices through two or more lines at distinct points is called a transversal. While a single intersection creates four angles, this transversal creates two separate points, giving us 8 distinct angles. Let's number them 1 through 8. We organize these into a top cluster with angles 1 through 4 and a bottom cluster with angles 5 through 8. This 8-angle matrix is the result of any transversal cutting through a pair of lines, giving us a specific set of intersections to analyze. Take a look at these 8 angles. Is it possible for every single one of them to have a different numerical measurement? We can find the answer by looking at the intersections individually. In the top cluster, angles 1 and 3 are vertically opposite, so they are equal. Angles 2 and 4 also match. The same logic applies below. Angles 5 and 7 are an equal pair, as are 6 and 8. Because these vertically opposite angles are always tightly tied together, a transversal crossing two lines will produce a maximum of 4 different angle measures across the whole set. Now, let's see what happens if we make the two horizontal lines perfectly parallel to each other. Notice the positions. Angle 1 is in the top left corner of the upper intersection, and angle 5 is in the top left corner of the lower intersection. These are called corresponding angles. If we take a tracing of angle 1 and slide it down the transversal, it fits perfectly over angle 5. They are the exact same size. Based on that same positional logic, can you identify the matching twins for angles 2, 3, and 4 in the bottom cluster? Angle 2 matches with 6, 3 matches with 7, and angle 4 matches with 8. When a transversal intersects parallel lines, the fixed incline ensures that every corresponding angle pair is equal. This relationship is how architects and engineers draw parallel lines. They hold a ruler firmly and press a triangular set square against it to draw their first line. Here, the ruler acts as the transversal. Because the set square has a fixed angle, sliding it down the ruler creates a second line at the exact same incline. Since the corresponding angles are equal, the two lines are parallel. Let's apply this to a numerical problem. In this diagram, a transversal crosses two parallel lines. If angle 1 is 60 degrees, what is the measure of its corresponding angle, angle 5? Think about their shared positions and leave your answer in the comments. By tracking these relationships, you can determine unknown measurements across the entire matrix and use geometry tools to create parallel lines with accuracy.